multivibrators. Multivibrators are also the circuits with positive feedback. There are three types of multivibrators. One is bistable multivibrator, second one is astable multivibrator, and third one is monostable multivibrator. We'll see all the three multivibrators, but there are very rare chances of questions on these multivibrators, but still there are some questions in gate examinations on these multivibrators. We'll see one by one all the three multivibrators. First, bistable multivibrator. Bistable multivibrator circuit will be important for the examination. For bistable multivibrator, the output will remain at one stage, for example at plus Vsat. If output does not change from plus Vsat to minus Vsat with its own, then we can say that for this circuit plus Vsat is a stable output state. And if we make some changes in the circuit so that this output changes from plus Vsat to minus Vsat, and if output remains at minus Vsat, it does not change with its own from minus Vsat to plus Vsat, then we can say that minus Vsat is also a stable state for this circuit, and a circuit which have two stable output states is called as bistable multivibrator. Circuit is simpler for this bistable multivibrator. Circuit is much like Smith trigger, but in this circuit we have this input grounded. Now if we calculate this voltage VB, then VB comes out to be V0 into R1 upon R1 plus R2. There is no reference voltage, so V0 into R1 plus R1 upon R1 plus R2. This is the equation for VB. Now we don't know the value of VB here. Initially, if we assume that both the input voltages are at same potential or output is equal to 0 initially when output is equal to 0, then VA is grounded, and if V0 is 0, then VB will be also at 0 volt. So both the voltages will be at 0 volt. Now due to the noise present in the system, either VA or VB will be greater than the other. So due to this noise, the output voltage will either be plus Vsat or minus Vsat. So if we assume that V0 equal to plus Vsat, due to noise VB becomes little greater than VA and output becomes plus Vsat. And if output is equal to plus Vsat, VB becomes VUTH, which obviously will be positive. And if VB is positive, VA is 0, VB is greater than 0, which means VB is greater than VA and output will be positive. Now in this circuit we don't have any element like which can change the difference between VA and VB, means which can make VA greater than VB, so output will always remain on plus Vsat, means plus Vsat is a stable state. Now if we apply a negative pulse at VB, which will be making this VB voltage below 0. If this VB voltage goes below 0, then output goes to minus Vsat. And if output goes to minus Vsat, Vb becomes VLTH, which is obviously negative for this equation. If it is negative, then Va is 0, Vb is negative, and output will always remain at minus Vsat. So for this circuit, minus Vsat is also a stable state. For changing the output, we will have to again apply a pulse at Vb. This time we will be applying positive pulse at Vb. So this is the bistable multivibrator. Uh, mm, this circuit is important for examination point of view, and based on this circuit, questions may be asked. Next is astable multivibrator. The circuit for astable multivibrator will be like this. Now we will see the operation of this astable multivibrator with the help of these diagrams. Initially we assume that output V0 equal to plus Vsat. If output V0 is equal to plus Vsat, then VB equal to VUTH. We have drawn these two levels, VUTH, VLTH, and on this graph we'll be drawing the voltage VA, or it will be equal to VC, that is voltage across the capacitor. Now we'll start the analysis. Initially we have assumed that V0 equal to plus Vsat. If V0 equal to plus Vsat, if V0 equal to plus Vsat, then this RC network will have a positive voltage here, and current will flow in the downward direction. If current is flowing in the downward direction, capacitor will be charged with the polarity shown in the figure. If capacitor charges with this polarity, then VA voltage will rise like this. And if while rising VA crosses VUTH, if VA crosses, which is the present value of VB, if it crosses VUTH, then when VB crosses VUTH, sorry, this voltage VA crosses VUTH, at this point VA becomes greater than VB, and if VA becomes greater than VB, output at this point changes from plus Vsat to minus Vsat. Now as soon as output becomes minus Vsat, then this RC network will have a negative voltage at this point. Now the ground potential is greater than minus Vsat, so current will flow in the opposite direction. Earlier the capacitor was charged with this polarity. Now when current flows in the opposite direction, the capacitor will start discharging and capacitor voltage becomes 0. And after discharging, the current still flows through the capacitor, which charges the capacitor with opposite polarity. If capacitor charges with opposite polarity, Va becomes negative. If Va becomes negative and if it crosses VLTH, which is the present value of VB, when output changed to minus Vsat, VB changed to VLTH. So when Va goes below VLTH, that is VB, at this point Va becomes less than VB, and at this point the output changes from minus Vsat to plus Vsat. So in this circuit we have seen that we are, without doing anything, this circuit is generating a square wave, means we are not changing anything in the circuit. The output is continuously changing from plus Vsat to minus Vsat and minus Vsat to plus Vsat. So this circuit is an unstable multivibrator which does not have any stable state at the output, because output by itself changes from plus Vsat to minus Vsat and minus Vsat to plus Vsat. So this is an unstable multivibrator, and commonly it is known as a relaxation oscillator or a square wave generator. Circuit is important here. It is also called as square wave generator. In this square wave generator, the one cycle is completed here, or this is the starting part of the waveform. So when it goes to minus Vsat again, this is the one cycle of the output waveform. In this output waveform, we can say that the charging and discharging of capacitor, if capacitor charges discharges fast, then curves will be like this. So the output waveform will be a bit compact, and that is the time period reduces and frequency increases. So the frequency of the output depends on this RC time constant of the capacitor, means this R and C, product of R and C, this is called RC time constant, and based on this RC time constant we can change the frequency of the output. Now the last one is monostable multivibrator. Monostable multivibrator, the circuit will be similar to a stable multivibrator with little difference. This is the circuit of a stable multivibrator, and we will connect one diode across this capacitor. Now in this monostable multivibrator, as we have seen in the unstable multivibrator, this capacitor will be responsible for change in the output by its own. So we'll start the analysis that the voltage at non-inverting input will be equal to V0 into R1 upon R1 plus R2. Initially we assume that V0 equal to plus Vsat. If V0 equal to plus Vsat, this voltage will be plus Vsat and this voltage is 0. For this diode, the anode potential is greater than cathode potential, so this diode will be forward biased, and if this diode is forward biased, it will be replaced with a short circuit, and if this diode is replaced with short circuit, the capacitor will be shorted from across and will not be able to charge. So we'll now see the waveforms. Here we'll plot output voltage, here we'll plot VA equal to VC, this is VUTH and this is VLTH. We will be comparing VA and this VUTH and VLTH. Now initially we have assumed that output equal to plus Vsat. If output equal to plus Vsat, the capacitor is shorted from the across and capacitor does not get a chance to charge. If capacitor does not charge, the output does not change and output remains at plus Vsat. For changing the output, we'll have to apply a negative pulse at VB. If we apply a negative pulse at VB, we have earlier seen in a bistable multivibrator. If we apply negative pulse at VB, this pulse will bring the VB voltage below VA. If VB becomes below VA, output changes from plus Vsat to minus Vsat. For short period, the output has come to plus Vsat, minus Vsat from plus Vsat. Now as soon as output goes to minus Vsat, this voltage becomes minus Vsat. Diode D becomes reverse bias. If diode D is reverse bias, it will act as open circuit. If diode acts as open circuit, the capacitor now will get chance to charge. Now the RC circuit will have negative voltage here and a current will flow in the upward direction, and due to this current the capacitor will charge like this. If capacitor has this polarity, the voltage VA at this point, this voltage VA goes to negative. Now up to this point the capacitor voltage was 0, and after this the capacitor start charging in the opposite polarity, so the voltage is going negative. When capacitor voltage crosses this point, means VUTH, here VA becomes less than VB, that is VUTH, and at this point the output again goes to plus Vsat. And if output again goes to plus Vsat, it has reached its stable state again, and this state is called unstable state or quasi-stable state. Unstable or quasi-stable state. Quasi-stable state. So in this circuit, the output of the circuit was at plus Vsat, and when we applied a positive pulse at VB, output changed from plus Vsat to minus Vsat. After some time the output again becomes plus Vsat itself. So for this circuit, plus Vsat is a stable state and minus Vsat is a quasi-stable state or unstable state, hence it is called as monostable multivibrator. A monostable multivibrator, we can see that here voltage VB, at this VB we have applied a pulse, negative pulse, and at the output we have got another pulse. If we compare these two pulses, the time period of the pulses, if we compare the time period of the pulses, the time period of the pulse at the output is very large as compared to the pulse at VB. So this monostable multivibrator is also called as pulse stretcher circuit. We can stretch a pulse which is applied at VB, and the stretched form is obtained at the output. Some characteristics of operational amplifier. Already we have seen some characteristics, but these characteristics will help us to compare the operational amplifier, practical operational amplifier, with an ideal operational amplifier. First is CMRR. It is called common mode rejection ratio. Earlier we have seen that For an operational amplifier, it is operated in open loop condition. Then it generates an output V0 equal to AOL into V2 minus V1. If you apply here a voltage 450 millivolt and 500 millivolt, the difference is around 50 millivolt, and this 50 millivolt difference will be amplified, so we'll get some output. Now if we change this input to 500 millivolt and 550 millivolt, again the difference is 50 millivolt, so in this case also the output should be equal to the output value in the previous case, but practically the two values of output are different. So from here we conclude that output of the operational amplifier is not equal to this, but we will try to compensate all the difference in the output which are uh, all the changes in the output equation. We will try to compensate all the changes so that output equation becomes equal to this. But practically the output equation is AD into VD plus AC into VC. This AD into VD is called differential output, which is we are considering up to now this, and this is additional output which is called common mode output. This is differential output and this is common mode output. AD is called differential gain, and this differential gain is our open loop gain which we have considered up to now, and VD is equal to V2 minus V1. AC is called common mode gain, while VC is called common mode voltage, and it is the average of the two voltages applied at the input. So this is the exact equation of the output. From this equation we can define CMRR. CMRR is the ratio of differential gain to common mode gain. In the output, the common mode output should be absent. The output should be equal to differential output. For this we have to decrease this AC to reduce this AC to 0. So for ideal op amp, AC tends to 0, so CMRR tends to infinite. For ideal operational amplifier, CMRR equal to infinite. Now the operational amplifier has its first stage as a differential amplifier. Emitter coupled differential amplifier. This will be the first stage of an operational amplifier. This is the first stage of differential amplifier. For this differential amplifier, the common mode gain AC is inversely proportional to emitter resistance RE, while the differential gain is independent of RE. If it is independent of RE, AD is not affected because of RE. while AC is affected because of RE, so will increase the RE, AC will decrease, and CMRR will be improved. So to improve CMRR, RE should be as high as possible. Sometimes in differential amplifiers, in place of RE, a current source is used which maintains a necessary emitter current. Also, for this, internal impedance is high. If it is ideal source, internal impedance is infinite. If it is practical current source, then also internal impedance is very high. Now the next characteristics is slew rate. Suppose we have this operational amplifier. For this operational amplifier which is operated in non-inverting mode, we have applied an step input to this operational amplifier. For this operational amplifier, gain is equal to 1 plus R2 upon R1. The output should be equal to like this. If it is 1, it is A. Like this, the output should be generated. But a practical operational amplifier have some restrictions over the fast changes in the input signal. Here we can say that the input is 0 for t less than 0, and at t equal to 0 there is sudden rise of or there is a sudden step in the input. This sudden rise cannot be reflected as it is at the output of op-amp. The output looks like, means output cannot change suddenly if there is change in sudden change in the input. And for this output, if we mark 2 points on this slope, we get change in time dt with change in output voltage, and slew rate of the operational amplifier is defined as the change in output voltage with respect to change in change in time, its maximum value. Or we can define slew rate as it is the maximum rate of change of output voltage of op-amp. Now if we modify or make some changes in this expression, it can be written as dv0 by dvi into dvi by dt maximum. This dvi by dv0 by dvi is called gain of the operational amplifier. We'll use only magnitude here into dvi by dt maximum. If vi equal to vm sin omega t, if it is sinusoidal voltage, then after differentiating this we get dvi by dt equal to vm into omega m into cos of omega m into t. And dvi by dt maximum, we know that for cos signal its maximum value is 1, so dvi by dt maximum is vm into omega m. So now putting slew rate is equal to magnitude of gain into vm into omega m, and fm is equal to slew rate upon vm into 2 pi into magnitude of a, where omega m equal to 2 pi fm. So this, if frequency f is greater than fm, then output will be distorted. We have already seen in step signal there is sudden rise. Sudden rise means there is infinite frequency. For such a high frequency input, output will not be same as input, so there is distortion. If f is greater than fm, there will be a slew rate distortion. If f is less than equal to fm, then output will be free from distortion. Now we'll see some one example on slew rate. An operational amplifier has slew rate equal to 0.8 volt per microsecond. The input signal is 0.25 sine of omega t. The maximum frequency of input in kilohertz for which there is no distortion in the output is, the circuit is given. Options are given as 23.84, 25, 50, 46.60. The equations required to solve this problem we have already seen. From the given figure we can calculate its gain. As it is an inverting amplifier, gain A equal to minus 470 kilo ohms divided by 22 kilo ohms, which comes out to be minus 21.36, and magnitude of gain is equal to 21.36. Also, Vm is given 0.25 volts and slew rate equal to 0.8 volt per microsecond, which can be written as 0.8 into 10 raised to power 6 volt per second. Now we want to calculate the maximum frequency. Fm is given by slew rate upon magnitude of gain into 2 pi into Vm. Putting all these values, 0.8 into 10 raised to power 6 divided by 21.36 into 2 pi into 0.25, and this comes out to be 23.839, which is nearly equal to 23.84 kilohertz. Now next is input offset voltage. Suppose we have this operational amplifier and both the inputs are grounded. If both the inputs are grounded, then ideally the difference in the input is 0 and hence output V0 is equal to 0 volt. Now practically this output voltage doesn't remain at 0 voltage even if both the inputs are grounded. This means there is mismatch in the transistor. We have already seen this emitter coupled differential amplifier, which is first stage of the op amp. If both the transistor have different characteristics, then we get output even if both the inputs are grounded. So this mismatch in the transistor can be seen as a voltage difference in the input terminal, and this voltage difference is called as input offset voltage. Means there is a difference existing between the input terminals, so the output voltage is not zero. This voltage is called input offset voltage. There is another definition of input offset voltage. See, when both the inputs are grounded, we are not getting the output voltage equal to 0 volt. Means there is some voltage difference in the input. Now, if we apply a voltage source at the input terminal of op amp, polarity will be decided while doing this thing in a practical op amp. We are not getting output equal to 0. Now this voltage will be varied up to when output voltage becomes 0 volt. Now when output voltage becomes 0 volt, this applied battery voltage nullifies the difference in the input voltages, so this voltage is nothing but the input offset voltage, VIO. Next is input offset current. Input offset current. Now if we have both the inputs grounded and if if any current flows in the input terminals of op amp, that is IB1 and IB2, we can define the input offset current as IIO equal to IB2 minus IB1, their magnitude. Whichever may be greater, we are interested in the magnitude. Number sorry, this was number 4 and this is number 5. Input bias current. We have already seen these two currents which are entering the input terminals of op amp. For this circuit, input bias current is defined as magnitude of IB1 magnitude of IB2 divided by 2. Average of these two currents is called input bias current. Input bias current affects the output when feedback is provided. If this is the circuit RF R, then for this circuit the input bias current affects the output. We will see how. But to reduce the effect of input bias current, a resistor is connected in this arm called offset minimizing resistance, ROM, and its value is equal to RF in parallel with R1. Now the last is output offset voltage. If we have both the input terminals of op amp grounded, and if there exists any voltage difference between output terminal and ground, this voltage is called output offset voltage. Output offset voltage can be due to input offset voltage, if there exists any input offset voltage, then output offset voltage is called is can be calculated as AOL into VIO. This is output offset voltage. Now if op-amp is used in feedback, suppose we have this circuit. Here also both the inputs are grounded. If we want to calculate here the output offset voltage, then output offset voltage can be calculated as VOO equal to A into VIO. Here the gain will be equal to 1 plus RF upon R1 and will be multiplied with VIO. Second, the output offset voltage is defined because of input bias current, and this output offset voltage is equal to I bias into RF, this resistance RF.